In this tutorial, I want to show you how we get our kinematic equations for acceleration using our graph of velocity versus time. So we have velocity versus time. And this is only for constant acceleration. So we start at some initial velocity, and we end at some final velocity, vf. And the first equation we're going to develop is based on the slope. Now the slope of a velocity time graph is equal to the acceleration. And the slope is going to be the rise over the run. So here is our rise, which is the change in velocity. Now we use the Greek letter delta to mean change, and this delta v simply means to subtract the two velocities, the initial and the final. And our run is how much time has passed. And so acceleration, which is A, is rise over run, delta v over delta t. And that is our first equation. Now we can rearrange this by saying A is vf minus vi over delta t. And so if we multiply each side by the time, delta t on both sides, so that they cancel out on the right-hand side, I'll write it over here, we have that A times delta t is equal to vf minus vi. And if we add vi to the other side, we get that vf is equal to vi plus A times delta t. So our first equation can either be written like this, A is delta v over delta t, or we can write it as this, vf is equal to vi plus A times delta t. So that's our first equation. Our first equation is vf equals vi plus A delta t, or A is delta v over delta t. To get our second equation, what we want to do is now look at the area of a velocity time graph. So again, we have our initial velocity, and it goes to some final velocity. And we're going to look at the area between the line and the x-axis. Now, this area here is equal to our displacement, not our distance, but our displacement. If the area is above the time axis, it would be a positive displacement. And if the area is below the x-axis, that would be a negative displacement. So the displacement here is equal to this area. However, this is not a very nice shape. So let's break this into two different shapes. We have the bottom shape, which is a rectangle, and that area is going to be the length times the width. So it's going to be vi times delta t. So delta x is vi times delta t. That's the area of the bottom part, the rectangle. And we also have the area of the triangle on top, which is 1/2 the base times the height. Now the height in this case is delta v. So it is 1/2 delta v times delta t. So we have the area of the rectangle plus the area of the triangle. Now looking at our first equation, we'll rearrange the first part here, or I'm sorry, the second part of this equation. We'll rearrange this to say that, as a side note, delta v is equal to A times delta t. So that's just the first equation rearranged. And so we can now write the second equation. If we replace the delta v with A times delta t, we seldom write delta t times delta t, Instead, what we do is we write delta t squared. So that is our second equation. So let's write that down. We have delta x equals vi delta t plus 1/2 a times delta t squared. That's equation number 2. Now we can go back here though, and if we look at this equation, we can also write delta v as vf minus vi. And so now, instead of writing delta v, let's write it as vf minus vi times delta t. Then let's distribute the 1/2 and the delta t to both vf and vi. So then we can get delta x equals vi delta t plus, so the vf gets the 1/2 and the delta t, and the vi gets the 1/2 and the delta t. Now here we see that we have vi delta t minus 1/2 vi delta t. Well, that's the same as taking a whole and subtracting half. If I have a whole pizza and I take a half away, I'm left with half a pizza. So I'm left with 1/2 vi delta t plus 1/2 vf delta t. Now what we can do is again factor out the 1/2 in front and the delta t on the end. So factor out 1/2 on the front for both, and the delta t on the end for both. And what we are left with is vi plus vf. So that is our third equation. Delta x equals 1/2 vi plus vf quantity times delta t. Now we look for our fourth equation. And to figure out the fourth equation, we're actually going to combine the first one here and the third one down here. So let's look at the third one. Delta x equals 1/2 vi plus vf times delta t. And the second one, the first one we're going to rearrange as delta t equals vf minus vi all over a. So the second equation, or the first equation here, we are going to subtract vi to the other side and then divide by the a to rearrange it as such. So we are going to replace delta t in the third equation with vf minus vi over a. Now one of the things I'm going to do here is I'm actually going to flip these two around. I'm going to say vf plus vi. The commutative property says that it doesn't matter which order you add numbers. I can either add 3 plus 4 is 7 or 4 plus 3 is 7. And then I have vf minus vi all over a in place of my time. Now we're going to rearrange this equation to make it look a little nicer. We're going to clean it up. So the first thing I'll do is multiply by 2 on each side and also by a on each side. Well, if I multiply by 2 on the right-hand side, it gets rid of the 1/2. And if I multiply by a on the right-hand side, it gets rid of the a. So I'm left with vf plus vi times vf minus vi. Now we can use FOIL to multiply and distribute these two terms, and what we'll get is the difference of their squares. So we have VF squared minus VI squared. And then we can add VI squared to the other side. So if we add VI squared to the other side, we are left with VI squared plus 2a delta x on the left-hand side, and we're left with VF squared on the right-hand side. Now a lot of times we'll flip this and write it as, instead, VF squared equals VI squared plus 2a delta x. So that is our fourth equation. VF squared equals VI squared plus twice the acceleration times delta x. So these are our four equations that we can use in kinematics when dealing with acceleration.